Yes, welcome to this presentation. My name is Eugene Twice, first year student at Material University. Today we shall be looking at history of computer generations as well as the Intel x86 and ARM architecture. Now to start off, we know that this computer generation went from the first, the second, the third, and later generations after that. So we shall first start with the first generation, where they used vacuum tubes for digital logic and memory elements. And for this study, we shall use the IAS computer, which was the first and most famous computer to use. This idea was first attributed to John von Neumann, who was a mathematician in 1945. Together with a certain man called Alan Turing, they came up with an idea which they wanted to use for this computer called EDVAC, which was the electronic discrete variable computer. Now, in this computer, as you can see the vacuum tubes, this is how they looked like. They were this big. They were actually big compared to the way they see them here. Now in these IAS computers, they had a structure which consisted of the main memory, which stored both the data and the instructions, the arithmetic and logic unit, which was capable of operating on binary data, and the control unit, which interpreted the instructions in the memory and also executed them. Then the control, the input, output, which was the equipment operated by the control unit. So as we shall see the structure was here, where we had the central processing unit as a whole, together with the memory addresses and the input-output equipment. Now inside the CPU, we had the arithmetic logical unit. In this arithmetic logical unit, we had the accumulator register, which is labeled as SC, the multiply quotient register, the arithmetic logic circuits, the memory buffer register, together with and those components consisted of the arithmetic logic unit. Then the other half of the CPU, we had the program control unit. In the program control unit, we had the program counter, the instruction buffer register, the memory address register, and the instruction register together with the control units. Now, as data was put, data started from the accumulator register. The accumulator register then went on to the arithmetic logic units, which continued to the memory buffer register. The memory buffer register contained the data that was to be stored in memory, and then it was sent to the input-output equipment, as you can see, which consisted of instructions and data from the memory buffer register. Then from the memory buffer register, it went all the way down to the memory address register together with the instruction register. Now the memory address register, as you can see here, it specified the address in memory of a word to be written, either to be written from the memory buffer register or to read from the memory buffer register. So you can see data from the memory address register sent data to the various addresses, as you can see here, and within those addresses there was the main memory. So data from the memory address register would pick data from the main memory and send them to the program counter. Program counter contained the address of the next instructions, which were to be fetched from the memory. Now, from the memory buffer register, data was also sent to the instruction register. Instruction register contained an 8-bit opcode that was being executed, and also data from the memory buffer register was being sent to the instruction buffer register. This instruction buffer register employed to hold temporarily the right hand instruction from the word in memory, and also the information from the program counter, from the memory address register, and from the information buffer register, together with the instruction register, was sent to the control units. and these components consisted of the program control unit. Now, as you can see in the next slide, from the first generation went to the second generation. This generation introduced the use of transistors. These transistors were smaller, cheaper, and they generated less heat as compared to the vacuum tube as we saw in the first generation. However, they were also used the same way as the vacuum tubes. They were also used to store memory and for processing, as we saw. So these transistors were invented by certain company called Bell Labs in 1947. So these transistors also brought about use of more complex arithmetic and logic, also control units, and also introduced the use of high-level programming languages and provision of system software with the computer. Member machines in this generation, or the machines used in the second generation, were the IBM 7094 and the 7000 series. As you can see, that's how the transistors looked. They were compared to the vacuum tubes, they were generally smaller. And also in the second generation, you can see that the main memory grew from the 2K, whereby this 1K represented 2 to the power 10 bits, whereby the vacuum tubes used 2K. However, the transistors that they created in this generation used 32K, which was 16 times big. And also, the time to access the 1 word of memory, or what we call the memory cycle time. In the first generation, they used 30 microseconds. However, the transistors could do this in 1.4 microseconds, so they were faster in accessing each word from memory. And this generation also saw improved electronics. For example, they introduced instruction backup, where they used to buffer the next instruction. Then, after the second generation, we saw the third generation. Here we saw the invention of integrated circuits. This was in 1958. Then before 1958, we saw that the generation computers of the second generation contained around 10,000, and as to increase their efficiency, they had to increase and put a lot of transistors to the hundreds of thousands. But this made manufacture really, really difficult. So they came up with an idea to introduce integrated circuits. And the computers they tested this on this generation were the IBM system D60 and the DEC PDP-8. So in this generation we saw what we called microprocessors. The microprocessors were small electronics, and they have been used up to this day, and they have been following a trend in their reduction in size as time goes on. The basic functions of computers are for the data processing, for storage, and also for control with the input and output. However, in this case, in the third generation, we also saw the introduction of gates and memory cells. Now the gates and memory cells, the gates were used to do the data processing, while the memory cells were used for storage of data. Now, it also consisted of the connections between the gates and memory cells. Also, these connections, what we call the buses, were also introduced in this era. So now, as you can see, data movement was passed through these interconnections, and then these paths also carried the control signals. For example, a gate would have like 1 or 2 data inputs and then activates that very gate. The control signal is on, the gate performs its function on the data inputs, and then it produces a data output. Also, when the control signal is off, the output line was null. So it would either lead to a write control signal or a read control signal. So the microprocessors became used later. They became used later in other generations, as we shall see. Then you can see also the gates and the memory cells. As you can see how they looked like. They also consisted mainly of silicon. They were made mainly of silicon and put in an integrated circuit. So data would put as input, and an activate signal would help it to produce output. Then the memory cell, as data enters, you could either read or write on the memory cell to produce output. And then in Moore's law, you can see a certain man called Gordon Moore in 1965 observed that the number of transistors that could be put in a single chip doubled every year. So if 1 year they could put 1 chip, the next year put 2 chips, then the next year 4, then the next year 8, like that. So the space actually somehow slowed down in the 1970s, and it started doubling every 2 years. This made, as time went on, the cost of the chip was falling down. This included maybe the computer logic and also the memory circuitry. So as you can see, as the cost remained constant, the number of transistors was increasing. So the chip cost was really reducing that time. And also the electronic path length was shortened, and hence this was increasing the operational speed. So as time went on, as they were increasing the number of transistors on the chip, they were also reducing the electronic path length, and hence the processor speed was increasing. That's why as time went on also, you could see as later generations, computers, their sizes was reducing. They were reducing. They were becoming more convenient and even more mobile. Instead of being in one place, as we can see now, we have laptops and smartphones which can be moved from place to place, which can be used anywhere. And also the reduction, you could see there were fewer need for power requirements. The amount of power that was being used to power these computers were reducing as time went on. And also we shall see in the later generations now, there have been other generations after the third generations. However, we no longer classify them according to the development of the types of processors, since after the third generation we still continue to use integrated circuits. However, we classify them now according to the advancement in the circuitry, in the integrated circuits. However, among these, we see large-scale integrations which contain more than 1,000 components placed on one single chip in the integrated circuit. Then we have very large-scale integration with more than 10,000 components per chip. In the ultra-large scale, which is being used today, ultra-large scale integration, which has more than 1 billion components that are put in a chip. Then we have semiconductor memory. In the 1950s and 60s, most computer memories were constructed from tiny rings of ferromagnetic material, which is like around a 16th of an inch in diameter. So the ring was magnetized one way, which was representing a 1, then magnetized the other way, representing a 0. So this memory at the time was fast, and it took a millionth of a second to read the bits stored in memory. However, at that time it was really expensive and bulky and used and also created destructive readout. Destructive readout, what I mean is the simple act of reading from the core would just erase the whole data that was stored in it. So it was very necessary to install the circuits to restore the data as soon as it had been extracted. However, the chips at that time could hold like 256 bits of memory. So since 1970, the semiconductor memory has been through very many generational changes, like around 13. We started with 1K, then the 4K, then 16K, went to 64, 256, the 1M, 4M, 16M, and now currently we have the 8 GB on a single chip that was used to process. So after the semiconductor memory, we are still on microprocessors. Now as time went on, more elements were placed on each chip, hence increasing the density of the elements on the processor chips. So Intel developed the first chip, which was called the 4004. After that, they came up with the 8008, which was twice as complex. Then after that, they made the 8080 made in 1974. It was the first general purpose microprocessor. It was an 8-bit microprocessor with richer instruction set and was faster and had a larger addressing capability. And also 16-bit microprocessors also were developed at the same time. until the 70s and had powerful general purpose microprocessors that included the 8086 and the 80386. And as you can see now from here, you can see various from 4004 in the 1970s. That's 4004, 8008, 8080, 8086 and 8088, and you can see they went from 640 bytes all the way to 1 megabyte. In 1980s, you could see that they even introduced cache in the 486 TMDX CPU, where they introduced 8 kilobytes of cache together with 64 terabytes of memory and 4 gigabytes of addressable memory. So up to these days, went to the 1990s where they introduced the Pentium and Pentium Pro, and recent where we introduced the Core 2 Duo and the Core i7 EE4960X that is being used to this day. Then I'm going to talk about the Intel 86 architecture. So this 86 architecture offers decades of effort in design on complex instruction set. It incorporates sophisticated design principles that were only found on mainframe and supercomputers at that time. So, as I was saying, the different processors in this Intel architecture, we have the 808, which was the first general purpose microprocessor, an 8-bit with an 8-bit data pass to memory. It was used in the first personal computer, which was known as Altair. Now, from there, we went to the 8086, which was far more powerful, and it was a 16-bit machine, had a wider data path, and larger registers. It had an instruction cache and a queue that prefetches a few instructions before they executed, and it was used in the IBM's first computer. And that is when it also brought about the appearance of the 86 architecture. And from then we saw the other extensions of the 8086, where we saw the 80286 that was addressing a 16 MB memory, the 80386, which was Intel's first 32-bit processor with an architecture that rivaled the complexity and the power of microprocessors that were made earlier, and the 80486 that introduced more sophisticated and powerful cache technology that also offered a built-in math core processor offloading complex math operations from the main CPU. Then we also went to the Pentium and Pentium Pro, where I introduced the use of superscalar techniques that allowed multiple instructions to execute in parallel. With the Pentium Pro, we went to the Pentium 2, Pentium 3, and Pentium 4 that also included additional enhancements for multimedia, floating point, and also added 70 new instructions designed to increase performance when exactly the same operations to be made on multiple data objects like digital signal processing and graphics processing. From Pentium, we went to the Core series where we had the Core, and it was the first Intel 86 microprocessor, which was a dual core that brought about implementation of 2 cores on a single chip. From Core, we went to Core 2 and increased the core architecture at 64 bits. And then more recent cores, from 2 cores, we have even seen up to 10 cores per chip, and also advanced vector extensions that provide a set of 256-bit and 512-bit instructions that increase the efficiency of processing of data. Then the ARM architecture, this was a processor architecture that evolved from the RISC designs and is used in embedded systems. So the products you can see are the Cortex-A, Cortex-A50, the Cortex-R, together with the Cortex-M. Now under the Cortex-M, we had the Cortex-M0, M0 Plus, M3, and the M4. So the ARM architecture became operational in 1985 and was used for internal research and development and was used as a coprocessors. Now these processors are used in ebook readers, consumer devices, home getaways, also modems, together with memory protection units and memory management units. Yes, that has been all. I remain Twice Eugene. I wish you good luck.